So welcome everybody to edition 273 of CACOR Live. Today we have a special presenter with us. Many of you will know her. Jean Dougherty has been around CACOR for a long time. Jean is a retired biologist and geologist with a long career with the Geological Survey of Canada. And if you mention that we are burning fossils, she will tell you that no, we're burning fossil fuels. So, anyways, Jean was in charge of the fossil collection that we had, Canadian fossil collection at one point. So, very interesting background. So today she will talk about the geology and why it's important, and she'll put that in context with the geology that we have here in the National Capital Region. So with that, Jean, over to you.
Thank you very much, Raymond, and thank you everybody for coming today. I hope that we can, I'll share my screen at this point. I hope that you can all see this slideshow from the beginning. There we go. So what I want to talk to you today about is the fact that geology really is an important science to people. They don't know it. It has many implications for their lives, especially the geology under your feet and in the places where you live, and how areas developed. But before we get on to this, what I'd like to acknowledge is the fact that Canada, we are speaking about the geology and the lands of Canada, which were first occupied by the First Nations, Métis, and Inuit people. And in particular, the area around the Ottawa Valley that I'll be talking about later on is in the unceded territory of the Anishinaabe and Algonquin peoples. The photographs and the information that I'm going to be talking about today can be found, a lot more information can be found in two different sources that I've worked here. One is called the CGen archive. CGen stands for the Canadian Geoscience Information Network, Education Network. And they have all of the Geoscape posters that you're going to be seeing today, as well as other information about the geology of Canada, written in particular for the general public consumption. So it's not a textbook on geology, it's information about the geology of Canada. The other is the Ottawa Gatineau Geoheritage group. We have a website where it actually outlines a lot of the sites that you could go and see where the geology is exposed in the Ottawa area. So this particular talk is going to be divided into two sections. The first section is talking generally about the geology of Canada and sort of some of the implications and issues that arise because of the geology of Canada. And I've put it down as different rocks, different places with different issues. And the Geoscape posters are posters that the geology community recognized a long time ago that people, especially in urban areas, really do not understand how important the underlying geology is to their everyday life, especially in terms of building codes and what they're going to be looking at, issues that are associated with the geology under their feet. So this was about late 1990s and into the 2000s. Geologists in especially Western Canada started the whole idea of these Geoscape posters, and they talk about the geology of specific regions and areas. And the second part of my talk, I'm going to use the Ottawa Geoscape poster as an example to how people can actually use these posters and the ideas that are encompassed there so that they can have a better understanding of the geology in their own area and how it affects them. So Canada is a huge country. Big surprise there. And we have a large number of rocks, different kinds of rocks in different parts of the area. This is a geologic map of Canada. And the big bullet in the middle is in the pink, is what is commonly referred to as the Precambrian Shield, the Canadian Shield, etc. And these rocks are the oldest rocks in North America. They form what we call the craton of North America, the central part of the North American continent. And in actual fact, some of the oldest rocks on Earth are found in the Canadian Shield. The documented, it's back and forth, the documented ones, the Acasta gneiss is just outside of Yellowknife, which is over in this part of the territory. And there is a new contender that could be there for the oldest rocks in the world found in northern Quebec. They are purported to be about 4.1 billion years old. The rocks of the Acasta gneiss are about 4.0 or 3.9 billion years old. And what I want you to see here is that the Precambrian shield in the middle of the country actually really has major impact of how things work across the country in a lot of different regions, a lot of different reasons. So for example, take a look at this. These are the watersheds that we have in Canada, and their susceptibility to changes in precipitation and flow regimes, and sensitivity that will result in things like drought and flooding and all that sort of thing. So it actually mimics very closely where the Canadian Shield happens to be. And that's because the rocks of the Canadian Shield or the Precambrian Shield have different characteristics on how water moves through it than it does in other parts of the country. The other thing I'd like you to note, you can see this in this map here. There's a lot of rivers and lakes and so on in the Shield territory, but there are many fewer in the areas that are especially in the prairies of Alberta. So you're looking at that, and those are the very major drought that you'd be looking at there. Another issue that's associated very closely with the geology under your feet and different things across the country are things like landslides. It makes particularly good sense that you're going to get landslides in areas like the mountain regions and so on. And that's where you're looking at the things here with the train wrecks that have gone through. And there's also places where human activity has actually induced landslides. This is an aerial photograph of the Frank slide that happened in 1903 in Frank, Alberta. And it actually was what had happened. They were mining coal in Alberta, in Frank, and they undermined a fault zone, and the whole top of the mountain came down and covered the village of Frank and killed over 100 people. The boulders, you don't really get an idea here, but many of the boulders in this particular part that covered the town of Frank are the size of Volkswagens. So they're huge, and many, many people were killed. And the other example that I've got here is a landslide that occurred just outside of the Ottawa region. You'll see more about this one, but it occurred in a completely flat territory. So it's flat there, but we got a landslide, and we'll explain why. Another thing that has risk in Canada that people need to know and understand a little bit are earthquake risks. Now, most people know about the Ring of Fire and the fact that we've got all these big earthquakes that could happen off on the West Coast. But what a lot of people don't realize is that other parts of the country also have earthquake risks. Maybe not as big an earthquake as you might get on the West Coast, but certainly earthquake risk in other parts of the lower risk. And I'll explain, especially in the Ottawa region, why we have certain things. I'd also like to point out that especially in this part of the country, the earthquakes that we see actually form along the river, the St. Lawrence River and up the Ottawa River. And there is a geologic reason for that, and I might get into that a little bit later if I don't cover it already. So these are the sorts of things that you're looking at. So in the late 1990s, early 2000s, the geology community put together a large number of Geoscape posters that are all available online at the CGen archives spot. And they cover different regions, different areas, and it's to explain the geology for those particular regions. In addition, we were trying very hard to make them so that they could be used as teaching tools for educators in schools, because most educators, like I'm talking elementary, senior, high school, not university, don't have the knowledge or don't have the expertise to understand the geology and to teach the science properly. So we were trying to put together resources for them that they could use. So for example, each of these Geoscape posters they follow roughly the same concept. What you have is a central image of the area that you're looking at. And around the image are going to be panels that will explain either geological concepts that people need to know. For example, geologic time is one of the things that is found in many of the posters. Also, things that would be impacting what has happened in that area. So glaciers, glaciations, water, where your water comes from, what water affects your water quality, and so on. So this is the example from Whitehorse. The one from Calgary. Again, you're looking at basically the reason from the prairies on the east part of the city through to the mountains and the city itself. And again, you're talking about various things that would affect different aspects of the country, of that particular community. And it varies from one part of the country to another. Another example, which might be interesting to people in the Toronto region, but also more widely in the Ontario region, is the Toronto Geoscape poster. And the reason I'm talking about what might be of interest to thing is that one of the aspects of the Toronto Geoscape poster is this panel talking about the Oak Ridges Moraine, which is actually where the green belt is in Toronto. And it is a natural source of water and filtration that can actually clean the water that's going in and flowing into the Great Lakes. So it's a natural system that probably provides hundreds of millions of dollars worth of filtration, that is a natural one that nobody has to pay for. But our provincial government is bound and determined to pave over that green belt. And there is a really good reason why they shouldn't. But hey, it's all about money. I won't get into the politics. Anyway, here's the example of Victoria. And in Victoria, one of the issues that people are interested in and need to know and understand are things like the subduction zones. You can see this, plate tectonics, how things are actually moving under the surface of the earth. And it has major impact on Vancouver and Victoria, where you're looking at earthquakes and so on. So these are the posters that you're looking at. And for the next part of this, I'm going to be focusing on the Geoscape poster for the Ottawa Gatineau region. And in this particular poster, we are looking, the central image shows an air photograph of the Ottawa River, and basically going from roughly Hawkesbury through to Arnprior and south to basically about Kemptville up into the Gatineau Hills. It's a fairly large region, but within that particular region, Ottawa has 3 different time periods of 3 different rock types, all within about a 10-kilometer radius of the Ottawa, Parliament buildings in downtown Ottawa. And the 2 parts up on the left-hand part of the poster, the deep time and different rocks, are the 2 things that are the 2 panels that are actually talking about the general geological principles that people understand so that they can make sense of the rest of the poster. And around the poster itself, there are different panels that are talking about things that might be important to people, like groundwater, earthquakes, landslides, things like that might actually affect their everyday life. And where are the risks and what are the problems that you have associated with these things. So as I said, we've got 3 different rock types of 3 different ages. And the picture that we've got here, you're showing the Gatineau Hills up on the top, and you're looking at the sedimentary rocks that we have underneath, near Hogsback and underneath Parliament Hill. And on the east end of the city, you have the unconsolidated muds and stuff from the Champlain Sea deposits. So we've got different landscapes, different land use that can be done with these things. So for example, on the east end is much more highly agricultural than on the west end of the city even, and certainly north into Gatineau. So each of these different kinds of rocks have different landscapes associated with them. So what we've got here are, I like to say the 3 W's, what, where, when these particular rocks formed and how where the geologic features were formed. So the rocks, the oldest rocks, now this is where I'm getting into my rule of 3s. The Gatineau Hills are igneous and metamorphic rocks that are 1,000 million years old. and I'm being very particular in the way I'm saying that, it's 1,000 million years old. The igneous rocks are rocks that form from a liquid rock. You normally call it a magma. It can cool very slowly under the ground and make lovely things like granites and quartzites and that sort of thing. And a metamorphic rock is a rock that was pre-existing, but it has been changed by temperature and pressure, any combination thereof. And the temperatures we're talking about are ones where it is not sufficient to melt the rock so it becomes igneous again, but it's enough to turn it so that things can actually change in the particular rock itself. So we get things like gneisses. And if you have a metamorphosed limestone, which I'll get into in a minute, it'll be called a marble because the characteristics of that particular rock changes with temperature and pressure. So it's 1,000 million years old, and those are the rocks of the Gatineau Hills. This is the dam on the Gatineau River. The sedimentary rocks that we find on the west end of the city and in the central part of the city under Parliament Hill are limestones, shales, and sandstones too, of 500 million years old. And these are the rocks that are the limestones and shales are actually indicating, and this particular type of rock also contains a large number of fossils, which tells us back 500 million years ago, Ottawa was a warm tropical or subtropical coral reef environment. And we have large, massive limestone deposits and so on, corals in there. And one of the things that we also recognize is that the kind of environment we're looking at is very much like the Great Barrier Reef off Australia. It extends for thousands of kilometers, and we find exactly the same fossils and exactly the same rock up in Baffin Island. So a lot of people, this is one of the indications that geologists had that back 500 million years ago, the ancient continent of North America was rotated 90 degrees from where it is now, and the equator ran south of Ottawa, or no, actually north of what is now the Ottawa region, and it has rotated 90 degrees so that the rocks of Ottawa are equivalent to and are the same type of rock as you've got up in Baffin Island, which is up in the Arctic Islands, for those of you who don't know where Baffin Island is. So again, 500 million years old, this is what the rocks look like. They're very large, nicely layered, the kind of thing that people talk about with sedimentary rock. And rock, I'd like to say for a definition, sedimentary rocks are rocks that form at or very near the Earth's surface. They can form in two different ways. They can form by chemical deposition out of seawater or out of water. So things like limestone and salt deposits are things that would be sedimentary and coming out from that way as a chemical precipitation out of water. It can also be sediments that are eroded away from other rocks and brought down in rivers and streams into lakes and ocean basins. So those would be the things that would form muds and shales and that sort of thing. So those are sediments that are accumulated and cemented together to make another type of sedimentary rock. So those are what you're looking at. The third age of rock and the different kind of rock type that we're looking at, or material type that we're looking at, are the unconsolidated muds, sands, and peats that we have on the east end of the city. And these formed 0.01 million years ago or 10,000 years ago. These are rocks or accumulations of material that formed just after the glaciers were here in Ottawa, and as they melted, they left behind these deposits. So this is what they look like. Beautiful farmlands. We have peat bogs out there. Mer Bleu is there. Alfred Bog, they are actually mining peat for agricultural purposes. So it is a resource that people use, but that's where it's found in this part of the world. So this particular chart is showing you the time periods that we're looking at. So the lowest ones in pink in the bottom is the 1,000 million year old rocks of the Gatineau Hills. And then we go, and there's a 500 million year gap between the Gatineau Hills and the Ordovician material that we find that are the sedimentary rocks under Parliament Hill and on the west end. And so and then we have another 500 million years of no deposition or no rocks found of this age between those rocks and the rocks that are found on the east end, the unconsolidated muds and sands. In between, we either have had erosion or no deposition of the rocks forming at all, but there was tectonic activity happening. So for example, in the middle between this time period called the Ordovician, the 500 million year old rocks, and the stuff that came from the glaciers, there was a whole lot of stuff happening around North America and so on. Like you had the continental collisions that formed the Laurentian Mountains and the Appalachian Mountains. And we have the remnants of some of those things here. We have a rift zone in Ottawa. We have a lot of rifted and broken rocks and faults. So we're in, if you look over on the one side, the Bonashir Graben, we have block faults and faults from tension as they were trying to pull apart a failed rift in the Ottawa region, and that's where the river flows. So one of the things that you just need to keep in mind is that things were happening, just we don't have the rock here to that actually explains what was going on. I'd like to focus on the youngest of this material because this has major implications for the general public in Ottawa. These are the rocks, the unconsolidated mud, sands, and rocks of the Champlain Sea deposits that we're talking about. 20,000 years ago, Ottawa was under about 2 or 3 kilometers of ice. This is the last big glaciation that happened in North America. We had a lot of ice here, and it pushed down, it weighed down the whole region. And so when the glaciers started to melt and recede, you had the depressed land that had been pushed down by the weight of the glacier. We actually had the Atlantic Ocean flowing up through the St. Lawrence Valley and up into the Ottawa Valley. And so we had the meltwaters coming off the glaciers. So you had the mixing of the fresh water and the marine water. So we ended up with this very cold, salty, but not fresh water, but not fully marine, Champlain Sea. And glaciers are famous for actually grinding up rock as it's moving forward and along. And there's a lot of rock and debris inside the glacier as it's melting. Those rocks are flowing, the material is actually flowing into the Champlain Sea. And this is where you get all of the muds and silts that you're looking at that form the bottom layers of this particular sea. In addition to that, there's also a lot of sand and rivers that are actually coming off of the glaciers, and it's depositing deltaic sands that we have in the Ottawa region as well. And so we've got this mixture of sand and silt and clay, and they are the top layers in the east end of the city, and they are not rock. They are not solid. So the lower part of this particular slide shows you the course of the Ottawa River in blue as it is today, but the red lines are showing some of the ancient bars and tributaries that might be, and the whole blue area, the light blue area, is actually the course of the ancient the ancient Ottawa River and parts of where the Champlain Sea deposits were. So now the Ottawa River itself, the river now is flowing through that particular area. And this has major implications because landslides are found. A lot of landslides are found in the Ottawa area, and it actually very closely relates to how close they are to the rivers in the system. So you can see up along the Gatineau River, along the Ottawa River, and especially down on the South Nation River, where there's these Lemieux and Castleman are talked about. This is a place where we get a lot of these Leda clay deposits that have become quite famous in the Ottawa area. Leda clay is the clay layers, lots of clay layers that we had from the Champlain Sea. They can look very solid. Those blocks, the 5 kilogram, 2 kilogram, etc., are all blocks of Leda clay. It looks quite solid. And in place where this knife is showing, that's an example of the clay. It makes good potter's clay, I'm told. I don't know. But in the middle, what you've got is if you mix up and stir the Leda clay or agitate it, it can actually flow. So everybody thinks they know what a quicksand is, but the Leda clay is what we would call a quick clay. So the clay, if it's disturbed, if it's agitated, it can actually flow. And the reason we get the landslides in places along the riverbanks is because the water or the clay has a way to flow out. So you can actually get undermining of the banks where the clay has been agitated and moves out. And that's what you're looking at, the clay here. I'm focusing in on this one section of the landslides on the South Nation River. Back in the late 1970s, the Ontario government recognized that they had a real problem with the Leda clay and the landslides that happen along the South Nation River. So they did a geotechnical study, and they came up with areas that were at very high risk of clay landslides happening that could be problematic. So in areas down near Segenberg, they actually were able to reinforce the banks of the river so that you aren't going to get the clay flowing out, so that the river is not going to disturb the clay. And you can see all along the South Nation River, all the different landslides that happened and how far back the landslides go and so on. And they identified an area in Lemieux where they recognized that they couldn't do much about it, but they realized that they had a real problem. And so what they did was, instead of reinforcing the banks of the river at Lemieux, they actually moved the town. So they took down the buildings and they moved them away from where there is a high risk of landslides happening. And this was done, and it was completed in 1992. So this is in 1993. There was a major landslide at Lemieux. You can still see up in the corner off on one of the blocks of land there's a square that looks a little browner than the rest of it. That's where the church was, that they were taking down a couple of years before that. This particular landslide is 680 meters long and 340 meters wide at the mouth of this landslide. What happened was there was a major in June. It happened in June, and there was a major rainstorm that came through for that particular weekend, and a lot of water was coming through, and it actually penetrated into the clay, and it acted as a lubricant, and the clay started to flow. So what you had was this landslide that moved down into the South Nation River and blocked the river for a few days. And it took a long while, took many weeks for this to actually move through and clear out the valley. But this was in some ways a major success because they recognized the risk and the hazard. But at the same time, there is still all through the Ottawa area and all through the actually through to Montreal and the St. Lawrence River, the same Leda clay poses a real hazard for people. So you have to understand that that's what you're looking at. So the issue, this is one of the things that happened in Ottawa. This is our National Museum of Natural History. It was originally the first home of the Geological Survey of Canada down in 1912. And we were actually exhibiting the specimens and the collections of the Geological Survey were in this museum building. And they had this lovely tower that they put on top. And within few years, they recognized that the tower was starting to pull away and sinking differentially into the Leda clay pod that was underneath the museum. And so what they did a couple of years after the museum opened, they had to take the tower down because it was destroying the front part of the building and it was pulling away. So the picture that you see in 2002 shows you the museum, how it looked afterwards, so that everything was about the same height, and the weight pushing down on the Leda clay pod was not going to cause major disruption. And then the Canadian government had to make a decision. The structure was old enough that they needed, it was about 100 years old, and they knew that they had to do some renovations to it. The question was, do you take the whole museum down and rebuild a brand new museum, or do you shore up the footings and put major footings down to bedrock through the Leda clay and shore up the building? And they made the decision to keep the museum and to shore it up. And they reopened it in 2012 after they had done the major renovation. They managed to keep the museum functioning while they were doing the renovations because it was all done subterranean work. And in 2020, what they've put up is they've put up this glass tower that is reminiscent of and about the height of the original tower that was put in. So this is to give you some idea of how high that tower would have been. So this was a direct result of some of the building problems you have when you're building in the Leda clay. It is a real problem. Another thing happened. We are building an LRT line, subway line in Ottawa. And through the downtown core, they decided not to put it on grade. They decided to tunnel the LRT through the downtown city. So this is right near one of the major shopping centers in Ottawa called the Rideau Center. And what happened was they were tunneling. They had built the tunnel. And then one of the diggers that was working there broke a water main. So all of a sudden you had pressurized water coming into the Leda clay, and it had a tunnel that it could go through. So the clay flowed, and it actually caused a huge pothole in the middle of the city. And it took, I can't remember how many it was, 13 cement trucks full of cement to try and fill up the hole. And then they could rebuild the tunnel underneath and repave the surface of that particular road. So potholes are a real problem where Leda clay is there. Likewise, building. This is a landslide scar on the left, 1950. This is a landslide scar of a Leda clay landslide. This is in a part of the city on just slightly east of downtown called Beacon Hill. And you can see in the red, marked off in the red, this is the outline of that particular clay slide. Once the clay has slid, it's pretty stable. But the material up on the ridges has not slid yet. So you are still at risk for landslides for the things that were built up on the top of those particular ridges in the landslide. So as a builder, you have to be aware of what your subsurface is. One of the other consequences of this clay, this is a pretty busy diagram, but I want to point out that the pink rock at the side on the left are the Precambrian shield rocks from Gatineau. They're resistant. There's not a lot of porosity and permeability, and water just flows off of it. And if it's in contact with the yellow rocks of the sedimentary rocks, the limestones, the sandstones, and shales that are true rock, it actually can go in and make an aquifer in the bedrock. The water can flow into those rocks, and it can be stored there as an aquifer. But it's a completely different story if you have overlying Champlain sea deposits. The clay acts like a barrier, so that the clay can actually act as an aquitard to water flowing through and into it. So it is water sheeting off, and the east end of the city can actually, it doesn't penetrate, and it doesn't manage to go into any sort of storage unless it happens to get into the sands and gravels that are part of the deltaic sands and stuff that are part of this particular Champlain sea deposits. But the thing to know is that the clay layers the quality of water is going to vary depending on where you get it out of those particular water resources. The Champlain sea, the Leda clay, is actually looked very solid in that one block that I was showing you, but it's being held together by salt crystals. So when you activate, and if you have a lot of water flowing through it, like they did with the South Nation River one, what it does is it leaches out the salt and that holds the clays together, and you end up with these clay layers liquefying. And the salt that was holding the clay together to make it look quite solid is actually leached out. So if you are getting water out of the sand aquifers that are part of the Leda clay Champlain sea deposits, you're going to have a very salty water, and it's going to taste awful. The other thing is that we've got peat bogs, we've got a lot of high organic material in there. The water is going to be smelly, and it's going to be horrible. The shales that we have in the Champlain, in the sedimentary units that are 500 million years old, many of the shales are very pyrite rich. And the pyrite can actually make it very smell like H2S gas that's coming through. So if you get leaching of the shales with the hydrogen sulfide or pyrite, that's what you're going to be getting. It's going to have a different quality of water for it. Likewise, the material that the water that's found in the sedimentary rocks is going to be hard water. It has a lot of mineral content to it. So you have to know that that's going to make a difference in some of your pipes and so on. You can get a lot of deposition of the scale that you get with hard water. Often it's calcium carbonate, which is limestone depositing on your stuff. So the Champlain Sea deposits are salty, discolored, and bad tasting. The water coming into the aquifers of the sedimentary rocks are actually potable water, but it could be hard water and could have problems that way. So yeah, there you go. Another issue in the Ottawa area that you need to know about is that we get earthquakes. Not big ones like they've got over in up on the west coast, but we have earthquakes nonetheless. As I said, the glaciers were very heavy and depressed the land. And what has happened is that after the glaciers have left, we are getting what is referred to as isostatic rebound. The earth is starting to gradually move up and again back to its natural position. And we have very low grade earthquakes. And instead of using the Richter scale, the kind of scale we use is more like the intensity scale. And I'd like you to note that along the Ottawa River and that we're looking at, we have a fairly high intensity kind of deposit where it shakes a lot. And that's where you're seeing a lot of the Champlain Sea deposits and the clay layers. And the intensity is the thing that you feel, because on the west end of the city, we've got bedrock. And if you think about it for a minute, if you shake bedrock, it'll move sort of as a single unit, and the intensity, you're going to feel it, but it's not going to be that intense. But if you have the clays and the sands of the Champlain Sea deposits, it's like a bowl of jelly, and you shake it and it's going to have reverberations, and you're going to feel it a lot more. So the intensity is going to be much higher on the east end of the city than it is to the west end of the city. And I'd like to point out that the dot there that says Ottawa, just to the west under the word Ottawa is yellow, so it's less intense. And the orange is the really intense part. That's where we've got a lot of the clays and so on. Whereas to the west end, you're starting to see more and more of the limestones and the bedrock there. So the landslide, the earthquakes, and how you feel the earthquake is really important. And that's also an important thing when it comes to building. You want to be very careful that you've built, as it pointed out with the museum, you have to go down to bedrock to stabilize things. Another issue that has some concern, occasionally you hear about it, is actually radon gas. And radon is a gas that comes off of the igneous and metamorphic rocks that are found up in the Gatineau Hills. Now, it is a gas, and it is one that has health effects that you have to be careful with. So in terms of radon as a health hazard for people, you have to know that it's a possibility, and you have to know that you have to be able to exchange the air in your house so that the radon gas doesn't build up. So if you're building a house in the Gatineau area, in the north of the city, please make sure that you have proper air exchange. And that's really, they became quite aware of this problem when people started to do energy efficiency and closing up their houses a lot back in the 70s and 80s. And they started to see issues associated with radon gas. Prior to that, houses were leaky enough that it wasn't a big problem, but it can be now. So that you're looking at the potential for those problems. So with that, I would like to say thank you for listening, and I would be happy to take any questions that people might have about, where's my stop share? There we go. I don't know if anybody has any questions or if I've bored you to tears.
There are a few questions. So first of all, thanks very much, Gene. That's very, very interesting to me, anyways, to learn about the geology. It's always fascinating to me how it's possible to figure out through geology what things look like billions of years ago, actually. So pretty cool. As the host, I get the luxury of asking you the first questions, right? So I've got a few questions I'd like to ask you. You mentioned the earthquake faults or the earthquake possibility. Do you have some idea of what the maximum intensity we could expect here in Ottawa, and when are we going to get the next earthquake?
The when is we still don't know the whens. In terms of the maximum intensity. 7,500 years ago, we had the largest earthquake in eastern Canada. We know it was 7,500 and it was felt in the area. And I'm trying to think what it was on the Richter scale. It was one that they did on the Richter scale. I keep thinking it was a 5 point something. Now, Richter scale, a lot of people, oh wow, a 5 or a 6. And recently there was a debate. There was the big earthquake off the coast of Japan in the last week, and there was also one on the north coast of British Columbia. And they were saying it's either the north coast of British Columbia, it was either a 6.9 or a 7.0. And 6.9, 7.6, it's like 0.1. What's the difference? But the Richter scale is a logarithmic scale. So the difference between 6 and 7 is 10 times more powerful. So with each gradient, you're getting more and more power for it. So the earthquakes that we have in Ottawa are relatively low. Back in, I think it was 2013, we had a 4.0 earthquake in Ottawa. This was when everybody cleared out of downtown core. Do you remember that?
Yeah, I clearly remember that earthquake. I was in the building downtown. Yeah.
I had the luxury of just landing in the airport just after the earthquake hit, and I got off the plane and was walking down the concourse in the middle of the afternoon. It was 2:00 in the afternoon, and there was nobody there. And I thought, what the hell's going on? And I got on the bus. I was taking the bus home, and I got on the bus, and everybody was talking about it. And it turns out that if you were in the east end of the city, you felt it like crazy because of the Champlain Sea and the jelly. But on the west end of the city, it was sort of a non-event. Right? It was like a train coming down. So the cause of those is, again, because of the isostatic rebound. And you don't know when the tensions build up in the Earth's crust. But the thing to note is that because we had this Bonnechere-Graben system that was developed back between the deposition of the sedimentary rocks of the Ordovician time period and the most recent, this is a failed rift zone. So the Ottawa River and the St. Lawrence River are actually part of what was a failed rift zone in ancient North America that formed about 250 million years ago. And that's why the rivers are flowing there. So the rivers especially in Eastern Canada, are flowing down fault zones.
Interesting. Actually, I remember very clearly that earthquake you were talking about. Like I was saying, I was in the building downtown Ottawa, and I had just actually arrived from San Diego the morning of, so it was very memorable. Actually, Peter's got a question, but Peter, if you could get prepared, I'll ask one other question while he's getting prepared. So you talked about the Canadian Shield, and I was wondering where would be the closest location for us to be able to actually witness the Canadian Shield.
The Gatineau Hills.
The Gatineau Hills, okay,
yes.
That close. Okay.
Carp Ridge. The Carp Ridge is an outcrop of the Canadian Shield rock. And I didn't mention that that's one of the things that you have to look at for radon gas. So we are right at the edge of the ancient craton of North America, and the Canadian Shield rock comes right out there. This was an ancient, I won't go into all the details, but that was right at the edge. 1,000 million years ago, this was the edge of the North American continent.
Cool.
So right here, we are at the juxtaposition between the shield and the not. The other thing, I didn't point this out on the geologic map of Canada, but the St. Lawrence River, on the north side of the St. Lawrence River, you've got shield rock. On the south side, you've got the sedimentary rocks. So again, the same kind of juxtaposition.
Okay, thanks. So Peter, you have a question, and I guess who will be next? You've got a few questions, so
okay.
So go ahead.
I thank you, Raymond. Very interesting, Gene. I'm always fascinated by geology, and especially our local geology. As you may or may not know, I have a background in geophysics and worked as a solid earth geophysicist in geomagnetism with the earth physics branch at EMR. Anyway, I also worked with Paul Hoffman.
Oh, good for you. Okay.
Yes, I spent quite a bit of time working with Paul. Anyway, I have two related questions, if you could. One is about the Grenville front, or back, depending on what you want to call it. And if you have any explanations as to the origin of that piece of rock on the north side of the St. Lawrence River is sort of separate from the Precambrian, the ancient Precambrian shield. And the second question I have is in regard to the Ottawa airport. As many of you may know, it's very flat out where the airport is. Well, in fact, that's on a salty, sandy flat that is the remains of the former sea that was there that Jean referred to. And I'm just wondering if you can add any more about when that sort of shores were formed and how long they were there before the seas retreated. Thank you.
Okay. With respect to the Grenville outcropping, the MAC that you're talking about, as I said to Raymond, on the north shore of the St. Lawrence River is shield rock, and the south shore is stuff substantially younger. And running down the middle of the St. Lawrence River is one of the major faults in the area. It's called the Logan Fault. Yes. Now, the Precambrian shield, I refer to it as almost like it sounds like it's a uniform rock that formed all at one time. It didn't. It is a whole range, a melange of various different geologic provinces that have all come together and accumulated, agglomerated over the course of about 3.5 billion years. So it's a whole melange of things that have mixed together. So how old the rock is and how it formed, I'm not all that familiar with it, but I can guarantee that it's at least 1,000 million years old. And chances are pretty good it's coeval or about the same time period as the rocks around the Ottawa River. So the edge, the one thing that, if you remember the geologic map of Canada, the pink's in the middle, and then there was yellow, and then there was blue, and then there were blue, and then yellow. And each of those the Precambrian shield is the oldest. The blue stuff around the edge of it is the next youngest, and then the youngest stuff on the outside. So the blues are the St. Lawrence lowlands. Those are sedimentary rocks that are about the same age as the material that we've got around Ottawa, the sedimentary rocks here. And then the yellow stuff out in the prairies and up into the Arctic islands, those are the stuff that is sort of the last 60 million years and younger. So I don't know the details of that particular unit, but I can guarantee that that's what you're looking at, something akin to that. How it got there, I'm not sure. Whether it was an ancient mountain or whatever, I don't know. But with respect to the airport, again, yes, what you're looking at are the sands. As I mentioned, they're deltaic sands that were sheeting off of and forming out from the glaciers as they were melting away. So you had these rivers, and the sand, it was flowing, so there was enough force, and the sands were actually coming out rather than clays. The clays would be further out into the basin, and the sands would be depositing closer in. And I don't know how many of you remember when they were building the houses right at the corner of Hunt Club Drive and Riverside Drive, that whole area right there on the Rideau River is all sand. The whole area there by the airport is one of those sand areas, and there's a lot of sand in that part of it. So it's unconsolidated, but it's pretty thick and reasonably stable. And because there's not a lot of clay, you're not going to get a lot of flow and landslides with it. You are going to get shaking, and you'll feel it with things, but it's a good spot to build something flat like the airport, and so it'll be pretty stable. The other thing to know about that building in those areas, that when they had to engineer the highways, the overpasses that they built on the east end of the city had to have a completely different kind of mechanical structure that they put together as compared to the overpasses for the 417 on the west end of the city. And what they had to do, especially at the Anderson Road overpass, they had to actually slope it very gradually, and they had to put floats underneath the stanchions that hold the bridge up, because it's built on clay, and the weight of the cars and trucks moving across that would be enough to destabilize the clay and move it. So they actually built support so that it would distribute the weight of the bridge and the traffic on it much further afield. So it's just another aside. The geotechnical problems that we have are quite substantial when it comes to dealing with the clay.
Yeah, so Peter had made a comment in the chat about the Nature Museum and the fact that they essentially built some stuff to make it float over the clay, right?
Mm-hmm. Yep, exactly. That's what they did. And they also put on the edges of the building, they put it down through the clay layer into the bedrock. Yeah.
Okay, so sorry, John Lang, I had mixed up the Johns there. So John Hall is next, and Claude, you're on deck after.
Thank you. I love geology, though I've never studied it. So I feel really I may have made a serious mistake in choice of career. That was beautiful. Thank you very much. Look, we're spending billions on the buildings on Parliament Hill. What do they sit on?
Okay, there is a major renovation going on at Parliament Hill, and they've dug a big trench around the Parliament buildings. And what they're actually doing is they're digging out and they're putting in a new gallery, public gallery and entrance into Parliament. Now, Parliament is actually sitting on quite stable bedrock, the shales and or the limestones and sandstones of the Ordovician material. But in addition to that, they are putting in the stanchions that they're putting in the gallery underneath. They are actually going to be doing earthquake resistant type infrastructure. Some of you, I think, are civil engineers that might be been involved in it. So they're actually digging a tunnel, they're digging a gallery, they're digging a parking lot, and they're putting in substructure that's going to make the Parliament buildings much more resistant to earthquakes as well. So yes, they are taking into account the fact that this is an earthquake zone, be it a small one, small earthquakes, but they're taking that into account, and they're building for the future so that the Parliament buildings, they're not likely to slip away like the Museum of Nature was, because it's definitely on bedrock.
So the Department of Public Works got something right.
They got a few things right. Yes.
Yeah, there's one other thing I'd like to mention. I work with radioactivity in my laboratory years. Radon is the last radioactive isotope in the decay chain from uranium, and it's the densest gas on the Earth. So a decade or so ago, the National Capital Commission, which was renting out a house in Gatineau Park, it was discovered that the basement, that's where the radon goes, it's dense, was so high they actually evicted the tenants and took down the house.
Yep.
So if you live in Gatineau, could be a really serious issue. Do you think any of the municipalities over there approving site plans for new development of housing know about? Oh, that's not a fair question, but
I don't know about, but I do know that it has been incorporated into the building standards for air circulation in the buildings and the refresh rates. They took it into account when it came to a lot of the sealing up and becoming energy efficient homes. So the air refresh rates, and it varies from one part of the country to another, depending on, again, things like the radon. So I think they know about it, but I think they're compensating with it by making the air exchange in the house better.
I think I'd opt for Leda Clay over.
So Meg Sears is on deck. So Claude, your question?
Yes, you didn't mention that I heard any caves, either limestone or sandstone, in the natural area there. And I was wondering, is that the earthquakes that collapse them so they don't have a chance to develop? And a related question is, what is the commercial depth in terms of floors down, where at some point it becomes uneconomical, so that they just build up instead of down? But I'm curious, and of course, I'm thinking in terms of survival space during extreme weather events in the future.
Okay. In terms of caves, there are caves in the National Capital Region. They're actually Bonashir caves that are sort of west and slightly north of the city. They're like a karst type cave in the limestones that we're looking at. So they're not associated with the Leda clay and that kind of stuff. So they are part of the Ordovician material, and it's the water flowing in the Ottawa Valley post deposition and formation of those rocks, and you do get the caves. So that's a short answer to that question. So yes, we have them. The in terms of depth for building, there is bedrock can be at the surface in Ottawa, and versus pods of Leda clay. It just so happens that the Museum of Nature was built on a pod of Leda clay. It's not a full unit. Like you have to realize that this was the base. This was the base of the lake, and it's not totally flat ever in a lake or an ocean. There's always going to be dips and so on. So what happened was that in the place where the Museum of Nature is, and it's 5 kilometers from Parliament Hill, something like that, and it's in a pod of Leda clay, and I think the depth of the Leda clay there is about 50 meters, might be less than that. And then it would thin out. And so depending on where you were and how big the pod would be, so it can be anywhere from non-existent, as in the west end of the city, and through to something as deep as 50 or 60 meters in the east end of the city. So I'm in an apartment on the west end of the city, and right next to us, they're building a brand new apartment. And every so often, I don't know, you guys have heard it, but every so often there's been and then because they're blowing up they're blowing it up and they're building the garage to go underneath the new apartment building. So does that answer your question?
It does. Sort
okay.
of highly variable
Yeah,
is
exactly,
a short answer.
Exactly. Okay. Yeah.
Thank you.
Yeah, just a short comment on that, Jean. The Museum of Nature is a kilometer or so, or barely a kilometer away from Parliament Hill. So it's really
I
not.
can't remember how far it is.
Yeah, it's not really that far at all. So we'll have Paul on deck, and Meg, it's your turn.
Great. Thanks so much, Jean. You mentioned earthquakes, and just up the river from where I live is Chalk River, and I believe there have been some earthquakes up there as well. So, and Chalk River is obviously where we have the nuclear laboratories, and the Canada still doesn't have a solution for long-term storage of nuclear waste.
No.
So they're still working on that. And in the meantime, they have the latest idea is to take all of the nuclear waste from Ontario and Quebec and to put it all at Chalk River. I'm still not sure where it's going to be a very large quantity. And sort of leave it there right beside the Ottawa River for undetermined amount of time, which will probably be a long time, while they get their approvals, and they're planning on doing some kind of deep geological repository in Northern Ontario. So I was wondering if you could comment on the wisdom of this location, pluses and minuses for storage of nuclear waste at Chalk River.
I would be, in terms of earthquakes being an issue associated with the Chalk River facility, I would not be too concerned about the earthquakes, because the earthquakes that they would be getting would be similar to the earthquakes that we get around Ottawa. And so it's on bedrock. And when I say bedrock, I'm talking the limestones, the Ordovician limestones. They're all around this part of the world. So it's bedrock, it's pretty stable. And so the earthquakes aren't as much of an issue as what I would think of would be flooding and water and issues associated with that. I didn't get into anything to do with flooding in the Ottawa River. That is dealt with on the Geoscape poster. And I don't know what the quantity of material they would be storing at Chalk River and under what conditions they would be storing it. So the biggest thing would be water in my mind. Anyway, that would be my first input, would be water infiltration into whatever the containers would be. But that's just a guess on my part. And so in terms of hazards I would think flooding and or water would be more so than earthquakes.
Thank you.
Okay.
Yeah.
Okay,
We
so,
have had earthquakes.
Sorry?
I live by Dunrobin, and we have had earthquakes here.
Absolutely.
So-
Yes, we've had many earthquakes in
Mhm.
this region, but they're small scale because of isostatic rebound from the post-glacial retreat. Yeah.
So you think that
It-
scale of, like, I don't really know about
They're-
the
they're minor.
hazards that can emerge from earthquakes when you've got something that you really want to keep watertight and stuff.
Yeah, well, it's more like a small shimmer rather than like the big one that you'd get on the West Coast. You're not looking at 7. You're looking at 3s and 4s on the Richter scale, which are quite minor. And most of the earthquakes we get in the Ottawa region, most people don't even know that they happen. It's occasionally that you get one like we did in 2013 or whatever it was, that we actually felt, and it caused a tremor with the downtown people.
Thank you very much.
Okay.
okay, so Art, you'll be on deck, and Paul, you have 2 questions, so you could go ahead and ask both.
Okay, thanks. Yeah, thank you. Very fascinating talk. I'm guessing in the Ottawa region, the deepest excavation was for the Diefenbunker. I could be wrong on that, but it goes down like 10 stories or something, or 5 stories. I don't know. It's very deep anyway. And if you have an idea as to how deep they went, like the tallest building in Ottawa is the one near just off Carling. It's and I wonder how deep they went for that, if you have any information on that. But my questions are, during the end of the last glaciation, all the meltwater was collecting in these massive lakes. So Lake Agassiz, which, covered Winnipeg and that whole region, was the size of bigger than all the Great Lakes combined.
Yes.
And then you have Lake Champlain over the Ottawa region. So I haven't seen anything written too much about what are the connections between those lakes? Were they independent watersheds, or I know that Lake Agassiz, when it drained, it caused meltwater pulses and rapid rises of sea level. The water drained northward into Hudson's Bay once, and then also it went southwards in another case into I guess out in, it went a different direction. And Lake Champlain, where did it drain and that sort of thing? I'm very curious about the connections. So that's the first question. And then the second one is the actual feedbacks and effects of climate change on landslides and volcanoes and earthquakes, for example. So the best example of climate affecting volcanoes is the Icelandic eruptions, right? Because the ice was melting back, it possibly relieved pressure on the earth. There was a lot of isostatic rebound, a lot of forces and pressures, and big volcanoes which shut down European airspace. Or the if there's a landslide on a volcano near the top, that can relieve pressure and the volcano can erupt. I think we've had some cases. I don't know if the statistics show larger volcanoes now happening. And then, of course, there's many other effects. So, I mean, of the heating, drying out of water tables, etc. So, for Cascadia, I think that's probably one of the biggest risks, sort of low probability, but if it happened, I think the last big eruption on the Cascadia was 1700. So, it's 300 years plus. It erupts every 200 to 400 years or something on average, with a major like 8 or 9 causing a massive tsunami. It could cause like 100-foot tsunami off the West Coast. So those are, I don't know. What are some of your thoughts on some of that? I mean, yeah, geology is fascinating. I like McGuire's books connecting climate and geology.
Yeah. Well, with respect to Lake Agassiz and the Champlain Sea, they are both, the connection is the fact that they're both related to the glaciers and glaciation, but they are formed in completely different ways. Lake Agassiz was formed with ice dams, and it was not meltwater coming off as much as it was areas that the glaciers actually closed it off, and you had the area behind was damming the water, so that when glacial Lake Agassiz was there, yes, it was huge and enormous, and it actually formed multiple times as the glaciers were moving, and you were getting closing off of these large lake systems. So as the ice dam melts or collapses, all of a sudden you get this enormous flow of water coming through the watershed, and it just goes like crazy. So yes, you're right. Glacial Lake Agassiz is definitely part of the geologic history of this part of the world, but it formed as ice dams behind the glaciers, so that it was not related to the Champlain Sea, which actually formed because the land was the glaciers were so heavy, it depressed the land, and the Atlantic Ocean flowed up the St. Lawrence River and into the Ottawa River. It went up about as far as Buckingham and into the Ottawa Valley. It didn't go much further up the Ottawa River. So you're not going to get the Leda clay and these things further up river from about here. This is about the furthest you go. So that they're totally unrelated in that sense, except they happened in about in the same relative time period and related to glaciation.
And it's if you've got 3 kilometers of ice, it'll push the land down about a kilometer. I think if you
I don't know what the ratio is, but
well, you just compare the density of ice to the density of bedrock.
That's right. Well, there's that
0.9 versus 3 or something, right? But, so it can be huge, and if the ice is sitting on the rock for a long time, it will reach that equilibrium. I don't know how long it takes. Okay, so that's great.
That's that. And with respect to climate change and volcanoes, I'm familiar with the kinds of things that you're talking about, but I don't know them in a lot of detail at all. With respect to the Ottawa area, the really big issue that climate change is going to have an impact on is our flow regimes and our flooding. And when I didn't talk about flooding in the Ottawa River at all, but normally we get 2 flood periods, 2 peaks of the floods when there's meltwater coming off from in the springtime. You get the first pulse, which is the local water that's just the snows that are melting locally, and it comes in and it's a pretty small peak. And then we get a second peak from all of the snows, the heavy snows that melt further upriver, Mattawa, Chalk River, all of that area up there. And the watershed, the Ottawa watershed, is quite large, and the snow melt coming in, and that's the larger pulse that we get. So the flooding that would happen normally in the Ottawa region associated with snowmelt is an issue, but we're also seeing a shift in when precipitation happens in Ottawa. It's starting to move up, so that if you start getting snowmelt and precipitation, large storms coming in, you're going to have major flooding in the Ottawa area, and that's going to be a real problem. But I do know that when it comes to volcanoes, back to your question about volcanoes, that the water regime that goes along with the volcanic eruption makes a big difference on how things work. That's about as much as I know. The question has been asked by people about water and so on, and plate tectonics and causing earthquakes and so on. Yeah, we think there might be an issue, but we really don't know. It hasn't been studied too carefully.
Yeah, I mean, for a climate changing volcano, you have to get the sulfur dioxide put into the stratosphere. So Mount St. Helens, the side of the mountain came off, like the eruption was from the side, up at an angle. Now, so I've always wondered, did the eruption start and then you got the collapse of one of the faces of the volcano, or was there a landslide on the face of the volcano first? And then that released pressure triggering it's like the chicken and the egg sort of. It's very interesting, fascinating questions. Anyway, thank you.
Yeah. Okay. No problem.
Just a little comment before we go to Art. I've been down that garage that you were talking about, Paul, at the corner of Preston and Carling, and they have 10 levels of parking there. Okay. 10 levels. So it's a very deep hole. So after Art, we'll have Peter. So Art, your turn.
Before Art asks this question, I want to say that particular building is on the Ordovician bedrock. Likewise, the Carp Diefenbunker. So none of those were in anything that was geologically unstable.
Okay, I've changed my question based on discussions going on here. I'm not as interested in geological time, at least long term, but much shorter term.
Mhm.
And given that Ottawa is built, a lot of it is built on top of laid of clay, we do have quite an intricate network of stormwater, sewage, and freshwater infrastructure that
Mhm.
is built, as it were, in some dynamic geological conditions. Um, and of course, this gets my attention because I know my house is built on laid of clay, and and this always has me a little concerned about. I keep trying to say to myself, I'm in a concrete ship, and it's floating
Big on mud.
on this mud. Yeah.
Mhm.
Anyway, um, can you address this infrastructure and stormwaters and sewage and fresh water? How big a problem is that, both in terms of design and maintenance with the city of Ottawa? Any feel for that?
I do know that the city of Ottawa did change their building codes. I can't say recently, but they did change their building codes about 20 years ago to look at the combination of earthquake hazards and geologic materials. So they did a major geotechnical study that was looking at just the kinds of things that you're talking about. So again, if you're in lead of clay and just a small pod, it might shake a little bit, but and it could cause cracking and stuff in your basement and infrastructure. But I do know that when it comes to connecting sewer lines and water lines, they are more, I do believe that they are using extension and contraction kind of jointing between them, so that they're taking into account freeze thaw is another issue that you have to deal with. And depending on your geological materials, how it reacts in the freeze thaw cycle is quite different. And so they do take it into account, as far as I know, but to what degree they do, I really don't know a lot of the building codes, but I know that they are definitely aware of it. And yeah, so they do try to take that into account. Other civil engineers might know more than I do on that, but yes.
Thanks. That's real interesting. I think I might go
Take a look.
and see what AI can tell me about it all. Yeah.
Please let me know if you find anything interesting.
Okay, so we have Valerie on deck, and then Peter, you have a question, but also I was thinking, Peter, maybe you can make some comment related to what Meg was asking about with those that nuclear waste upriver.
You're muted.
Do I have the floor now, Raymond, or
Yep.
has you got somebody else? Okay, thank you.
Yep.
Thanks for your continuing question and answer, Gene. I was wondering again, given this boundary between this along the St. Lawrence, as you're probably aware, there's Mount Royal in Montreal is the core of a volcano.
Mhm.
And if you stand up on the top of Mount Royal at one of the various vista points they have, you can look to the southeast, especially at near sundown, and you can see a series of volcanoes all
Yes.
the way into the distance. And I'm just wondering, when were obviously those volcanoes seem to be going over a hot spot of some sort because they're all in a line. But I'm wondering, when were they formed, and how long did that period last? And obviously they came through this Ordovician rock, so they must be more recent
Coming
than
through? No,
Ordovician.
no.
No?
Because this was the ancient continent of North America, it was above ground during the Ordovician. So the Ordovician warm tropical sea, it was just like the relationship between modern day Australia and then the coral reefs offshore. So the mountains that you're talking about and the areas on the north shore of the St. Lawrence are these at least Precambrian in age. Now, those volcanoes that you're looking at, geology, it's a real geological, and I can't call it a conundrum. They are working out the details of it, but yes, they believe it's related to a hot spot. They believe it could, there's also Mont Saint-Hilaire, which is in the same area. Geologically, it is one of the most unique places on Earth. There are minerals species that are found at Mont Saint-Hilaire that are found nowhere else. So what they're looking at is a type of magma or a type of system that was actually forming this absolutely unique geologic setting and causing the development of these minerals that nobody else knows anything about. So the whole geologic setting and working out that the dynamics in the shield rocks is much more complicated than it is in things that are flat lying and you sort of read it like a book. And you have to know that this piece of rock is related to this piece of rock and how much time is between them, because you can have juxtaposition of stuff that is millions and millions of years apart. So I can't answer your question directly, except that it is Precambrian. They are working at it. It's a unique geologic setting, and it's similar to, now, geology. I'm going to start talking geologic terms and sort of general geology. In a subduction zone, as the plates are coming together and one subducts under another, what you get is melting underneath and stuff coming up. So it's what you get are the volcanoes and stuff that are just behind. This is what Cascadia is. So you've got the subduction zone in Cascadia and Mount Baker and Mount Rainier and Mount Shasta and all of these coming down, just like you're talking about. It's a subduction zone. And so this is an island arc system that we are now beginning to understand as geologists, that this is part of a subduction zone and continents colliding and all these other things. So they're trying to work out, I don't know if it's a hot spot or a subduction zone. They have to work that out and see the relationship between all of the different volcanoes that are in there. So I hope that sort of quasi answers your question. I'm a paleo person, so I deal with the fossils.
Right, I realize that. It's okay. I'll let it pass. Thanks.
Okay.
Oh no, there was the follow on. It was about Raymond asked if I would speak a little bit about the nuclear waste. Yes, this has been a proposal by the government and partners now for about a decade. And that the site has been selected as primary site for Canada, has been selected to be in Chalk River. There's also a town in Ontario, I can't recall the name of it, but it's in northwestern Ontario, that has also taken a public plebiscite to also be willing to be a nuclear waste disposal storage facility. To put it in context, the nuclear waste that is being planned for either of these or both of these facilities I've just mentioned, and they're still, of course, being planned or assessed, it's relatively low grade nuclear waste. It's not the level of waste that you would have in a weapon. It's the level of waste you would have in medical equipment, for example, as well as nuclear power reactors. And the very point was being raised about the storage of nuclear waste. We think of it today as basically being in barrels of some sort in bins and stored in water around nuclear power plants. That's basically how it's been accumulated since we entered the nuclear age. And so there's still a long-term depository problem. But Canada is addressing it with respect to looking at suitable geological provinces to do that.
Okay,
and there is website information from various sources. I'm sure there's conspiracy sources as well, but I'm sure there are trustable sources, and I think I would recommend you could even look at the Canadian Nuclear Labs website, because they're also the Canadian Nuclear Labs, which is the main lab at Chalk River. There's about 3,000 employees there. They're also assisting the industry, and this is the international industry, who are making small modular reactors. And they're making their technical resources and labs available to industry for co-development and testing of small modular reactors. And Canada is a world leader in the refurbishment of nuclear reactors, which is refurbishing radioactive material.
Well, thanks a lot, Peter. So if John, if you could be on deck, and Valerie, it's your turn.
Jean, thank you very much for this. I remember last time you spoke to us and you were almost in an anecdotal way, talking about how you had decided where you would buy a house in Ottawa according to the geological conditions.
Yes.
It sort of prompted me when the LRT was being planned on the west side of Ottawa to ask what geological information had been taken into account in the decisions about the alignment. And I got no satisfactory answer. And now, of course, for a few years, people in this area have been suffering from a lot of shaking. You can't keep your pictures on your walls straight, and it can be very uncomfortable at times. I wondered, has this got anything to do with the geology that underlies us, or is it simply because the people who are ruining our lives here aren't very cognizant of what they are doing to us?
Yes. Okay. It has to do with the underlying geology, but it also has to do with how they have to do the work, or how they have chosen to do the work. In the west end of the city, the geology is basically, you're looking at the limestones, and they have to.
That's right. Yeah.
Have to haul the stuff out. They have to break it up. They have to drill it out. They have to either rock hammer or whatever. So, and the way in which they've decided to do the building of the LRT in the West End is they're doing what do they call it? Trench and fill, so that they actually trench out what's going to be the tunnel, and then they'll fill over, and they'll put the concrete in, and then they'll fill it over again. So it's a different process than what they did through the downtown core, where they were actually tunneling. And in the tunneling aspect, I do know without a doubt that I know the person who actually did many of the reports from Golder and Associates and so on. He was one of the experts in understanding the underlying geology in the Ottawa area based on various boreholes that we have around the city. And he was looking to try and help them target the tunnels so that they didn't hit too much of the lead of clay, that they wanted to be able to tunnel through something that is substantially rock. So in terms of what's going on in the West End, yes, you get shaking, and yes, you do, but it's just like you would get shaking in any kind of a circumstance, because what they're doing is so near the surface. As I said, right now, I've got the new LRT construction right in front of my building, and I have a new building going up beside me. And we're having blasts going on, and every so often you can feel the whole building shake. But yeah, it is what it is. And the LRT is going to make a huge difference for moving people around. So I keep my comments to myself and my mouth shut.
Thank you.
Because it's going to be needed. It's going to be needed. It's problematic. It's problematic, but it's going to be a short-term problem. That's all.
Short-term. We've dealt with it for 4 years now.
Yes.
And it just seems to go on. Even last week, I had to reset all my pictures.
Yes, absolutely, Val. And you got to realize I'm a geologist, so 4 years is nothing. Okay.
So,
Thank
John,
you.
I think you'll be the last question. So go ahead, John.
Thank you very much, Raymond. Jean, if I survive here, Jean, thank you. That was what I would call deep background to two things that affected me personally. One was why Sandy Hill, where I invested quite a bit of money in a house, had problems. Remember, it's Sandy Hill, had problems with Leda clay. Well, you explained that, and I learned that one brilliant engineer had figured out how, with a large drill, which he invented, could figure out the bearing capacity of that clay at certain depths, could be measured in terms of a new foundation.
Mm-hmm.
So that was important. And then second of all, how he did this is beyond me. He figured out how to transfer the load from this gigantic drill from the foundation, where he'd already spent money on my money on digging the new foundation. Now he transferred that to the new foundation, and so it is amazing. And then finally, I was involved when I was in arms control in foreign affairs. There was a woman who was very senior Secretary General to the UN Secretary General, convinced the Canadian government and public, and I was involved in learning from this, that one could bury radioactive material. So she went into quite a bit of the technicalities and did it so apparently convincingly that she went on to be the Secretary General of the what is it? Lieutenant Governor General of Ontario, and I've forgotten her name, but that's neither here nor there. But she was an impressive woman, and her case was a good. She made it very well. So, and for that, you really do need background as well.
Yes.
Of what's going on underground. Anyway, so thank you very, very much.
Thank you, John.
Okay, so now, Ted, if you could say a few final words.
I would be delighted to respond. Well, Jean's been a wonderful friend for a very long time, and she did a super job as the head of the organization for several years. I'm not a geologist, right? I've only been in places where geology is important. Just as when Val brought it up, yeah, I lived in New Zealand for 3 years, and during that period of time, we had several Force 6 quakes. And not only that, but I discovered I could not keep goldfish because every so often he'd wake up in the morning and all of the water would be on the floor. So the fact is that people do get used to living in earthquake zones. I also understand Leda clay. It cost me an awful lot of money to have the front half of my house glued back on because it is in the entire swamp that our suburb was built in, and they never told us about that. About half the houses in it need major repair. It cost me $80,000 to have the front 3 feet of my house glued back on. So yeah, one of the problems of trying to live in a place with Leda clay. Nowadays, apparently they actually pay attention to Leda clay. After one large subdivision near me had to have all of the houses bought back by the developer, and it was seen as being a violation of telling them that their houses would stand because within 3 years they were pretty well scattered around and falling down. So it is, the geology is useful to know. That said, Jean, wonderful presentation. And essentially the baseline for all the rest we're trying to do of let people live well on the planet. So I will thank you again for a wonderful presentation. And we will, of course, geology lasts a long time, so you can keep coming back as often as you want, for as long as you want. So thank you very much for coming. And I would now like to again prevail on all of those of you who are members. And now it's, well, another month or less, it's time to pay your annual dues. And that makes wonderful presentations like this available to you. And we would also ask you to share this with anybody else who is interested and let them come and join us as well. So thank you very much. And we can now turn our...
I'd just like to say thank you, Ted. And with respect to buying a house, I will say buyer beware.
Yeah. There you go.
Thank you, everybody, and thank you for coming, and thank you for the wonderful questions.
Thank you. And I'll stop the recording now, but if people want to stick around, we could perhaps